My name is Mike Mattera. Tell you a little bit about me. I've been involved in manufacturing since I was 17. I run machines. I was a CNC programmer. I did applications work. I did sales. I managed a sales territory. I taught at some colleges, taught programming and CAM. Ran my own business for a while, producing video training for a variety of CAM systems. And today, I'm here to talk to you about G Code Programming. The purpose of this little half-hour presentation is not to make you all into G Code programmers. That would require more than a half an hour. So what I want to do is to teach you enough so that if you look at a customer's program, if you're trying to help somebody solve a problem, that at least you have an idea of the framework of what it is and the components that make G Code. So you get an idea of how the control thinks so that we can get the right information into the post, into the control. And also, if you have a customer that is having a problem, with his post-processor, we can get the right information together to get to the post department so that they can quickly and easily modify that post form. So that's kind of it in a nutshell, what we want to accomplish here. So these are the things that we're going to talk about. I'm not going to go over all of these because I'm going to talk about all of these. So we're going to start off by talking about the origins of CNC programming. If you saw Julie's presentation yesterday, she had the little brother of this. This is a mid-1950s Kearney and Trecker machining center. Just a beautiful piece of, combined refrigerators that you could call a CNC control. A real giant and behemoth. But CNC machines started in the early 1950s as a result of the Air Force wanting to go higher, faster, further, more reliable. And back then, there were dozens and dozens and dozens of CNC, or dozens and dozens of machine companies just in America alone. And they all had their own great idea of how a CNC machine should work. And at some point, the Air Force got tired of that and said, no, you all need to come up with a set of standards on how CNC machines should work, and we need to have some cohesion of what this is all about. And since then, all CNC controls have been the same. And that's an example of sarcasm, because CNC controls are not and never have been the same. I think you'll find that there's probably about 5 to 8 codes that will be the same in all G Code type controls. Everything else, they're all, just like any company, they're all trying to be innovative and do the most with what they have to work with and create things that set them apart. And now when we have machines that are not just 3-axis mills, but are 6, 9-axis mills and lathes, you can bet that they're doing some pretty innovative things. Just an interesting little tidbit is the first programming system was called APT, which is Automatically Programmed Toolpath. So maybe historically you might want to look that up at some point, but that is the forerunner of the CAM systems that we produce today. So, G Code programming. Why alphanumeric codes? Why did they decide that this was the way to talk to a machine? Well, it's a simple way to define a motion or a function. It's also an easy way to declare a position, set a value, select an item, or to switch something on and off. And these are all things that you need to do with the machine tool. So there's 3 basic types of motion. We have linear motion at a rapid rate. We have a linear type of a feed move. And we have circular moves. And these circular moves can be clockwise or counterclockwise. But those are the 3 basic types of motion. And everything that a CNC machine is going to do is based on these 3 types of motion. They may combine those to group them to do special things, but everything is going to be rapid, linear feed, or circular. So again, why G code? What made them pick that? Well, there's certain things that we understand. If someone says red light, we know that red light means stop, right? If someone says green light, we know green light means go. Why? Because somebody told me that that's the way it is, and I follow the rules. That's what it is. I also like to think that when they decided to use G0 as a linear rapid move, that they picked it because it looks so much like go. Why not? I like to think it, but I don't think that's why they picked it. Linear feed, G01. Well, I like to think that they picked that one, or it helps me to remember it because I see that 1 as being kind of a linear move. Just helps me to remember it. Circular, G2. Well, a 2 has the one circular loop, so I think of that as being clockwise. And the circular counterclockwise, G3, has 2 loops, so I think of it as counterclockwise. It's just how I remember it. It's just a way of associating something to the code. But again, it's just somebody decided that this is what it is, and we all agreed to that, and that's the standard. Just like red means stop, and green means go, unless of course you're in Fusion, and then there's a red arrow at the beginning or the start of the cut, and there's a green arrow at the end of the cut. And I brought that up to Mark, and that's open for future discussion. But anywhere you go besides that, red means stop and green means go. So, typical CNC machine codes. This is what you might see for a typical G code line. So G generally defines motion. I mean, it has other functions, but generally you're telling it how you want to get to where it is that you want to go. X, Y, Z, we're using that to declare the actual position that we're going to. And then we're using F to set a value for a feed rate, and S to set a value for a spindle speed. And we're using T to select our tool, to select an item, which tool we're going to be using in this job. And then we use an M for a miscellaneous function. And miscellaneous functions are used to turn things on and turn things off. There's a variety of things that you may want to turn on and off on a machine tool. So with just what we've learned so far, you should be able to look at this line of code and get a general idea of what's going on. So we got a G1, so that's a linear feed move. We're going to this XY position. That's my feed rate. I'm using tool 1, and I'm going at a spindle speed of 500 RPM. So the only one we don't know is M3. And usually the case is with miscellaneous functions that you just have to get the chart that goes along with that particular CNC control. Although I've created a list here of some of the most common miscellaneous functions, you'll find that most of the ones that are on this list will be in just about any machine that you encounter. So for our M3, we're going to do a spindle, turning the spindle on in a clockwise direction. And those are common: spindle clockwise, counterclockwise, spindle stop. M6 is a tool change. M8 is coolant on. M9 is coolant off. These are all pretty common in most controls. But they don't have to be, because every builder can do his own thing, and he can make anything, do anything he wants. Next I want to talk about modality. And this is pretty basic. If it's on, it stays on until you turn it off. Okay? So if you have kids, you'll be familiar with this concept. So your kid goes through the house, and as they pass through each room, they turn on the lights. A light is a modal condition, right? When you turn on a light, it stays on until someone turns it off. They move from room to room, and they turn on all the lights until it seems like every light in the house is on. And then at some point, you will come home from work and move through those rooms and turn those lights off. So that's a modal condition. It stays on until you turn it off. But in this case, there's another variation of that where you can also set a different function to deactivate the previous function. And that applies with what we have here. So we have our rapid, our linear feed, and circular clockwise and counterclockwise. It's really not possible to do all of those at once. So if I'm going in rapid, I can't simultaneously be going in feed. So if I program a line and say G0 XY position, it's going to wrap it to that position. If I give it another XY position, it's going to wrap it to that position because G0 was the last programmed modal condition. If I say G1 with an XY position, it's going to feed to that position. And then I can just say XY to a new position, and it will feed to that position because it was the last programmed condition. So in this case, any one of these will deactivate the other. That's modal. We also have something called CAN cycles. And these apply, in this case, for G80 through G89 as drilling cycles. Now, I want to think in terms of manually drilling a hole. So when you manually drill a hole, basically what you want to do is move your part or move your tool over to where the part is. You want to move down to some clearance height above the part, and then you're going to grab that handle and you're going to feed down into the part until you get to your depth, and then you're going to wrap it back out of the part. Okay, so essentially that's 4 moves, isn't it? I had to move to the start point, 1. I had to move down to my clearance height, 2. I had to feed to my depth, and then I had to wrap it back out. Well, that's a lot of programming for just one hole, isn't it? So now if I have to do 500 holes, that would be a lot of code. So that's why we have CAN cycles, because a CAN cycle will incorporate all the motion that it takes to perform that function. It'll feed to depth and wrap it out. So again, it goes to the point, feeds in, wraps out. Basic drilling. And then we have something called a peck drilling cycle, which will take multiple steps to get down to depth. This is also called a deep hole drilling cycle. Now imagine if you had to program that with all those G0 and G1 moves. So let's say I want to go 2 inches deep and I want to take an 1/8 inch per peck. I'd have to feed in, wrap it out, wrap it back to where I left off, feed in again, wrap it out, wrap it back in, good. Huge opportunities for mistakes. It's real easy to wrap it in to the next depth rather than feeding to the next depth. And I can tell you that that's a possibility because I've done it. I've programmed controls that didn't have CAN cycles. And the worst part about not having a CAN cycle is you get all that program and then you realize, you know, I should have taken 100 thousandths per peck instead of 125 thousandths per peck. Then you got to reprogram the whole thing and then add an extra who knows how many lines to it. Again, a whole new opportunity for mistakes. Another type of CAN cycle is a counter boring cycle where it'll feed in, dwell, and then feed out. And what that does is when it gets to the bottom, it polishes up the bottom of the hole a little bit. So if you're putting a screw in that hole, it has a nice flush, flat surface to sit on. So this is not all of the cycles that are available. This is just an idea of what a CAN cycle does. So here is a tapping cycle, and this is going to feed in, the spindle is going to reverse, and then feed out. So it's basically screwing itself into the hole, and then screwing itself out of the hole. So it makes threaded holes, so you could put a screw in that hole. So these are CAN cycles, and that's basically what they do. They save you a lot of extra programming code. But again, they're still all based on that linear feed and linear rapid motion. Now the great thing about CAN cycles is they are modal. So once I describe that CAN cycle, all I have to tell it from then on is the next location. So I don't even have to describe all of this every time. I mean, this in itself is a huge saver of space and code. But now all I have to do is give it the next XY location. So in that case, it'll go to the first hole location. And it'll do the G81 from a clearance height of 0.1 to a depth of -1/4 inch. And then it'll go to the next hole and the next hole. And then when it's done, it does a G80. And you'll find with a lot of these types of CAN cycle groups that there's always a zero, what I like to call the zero code for the group. And the zero code for the group is the one that turns it all off. Because it's modal, every time it moves, it's going to drill a hole. It's going to move and drill a hole, and move and drill a hole. So there has to be something to tell it to stop, and that's what the G80 does. So here's an idea of some of the code groups. Code groups allow you to have multiple codes on the same line, but only one code from each group. Because like I said before, you can't have a linear feed and a linear rapid at the same time. You have to do one or the other. So I can have one code from this group. So maybe I'm drilling a hole. Well, I can't be basic drilling and peck drilling at the same time. Pick one. I can only have one code from anything in that group. These are basically motion codes here. And then we have a section here for plane selection. So G17, 18, and 19, pick which plane we're going to contour in. As a default, with most CNC controls, you'll be contouring in the XY plane. We normally think of cutting around circular this way, but you could cut circular in YZ or circular in XZ. So by telling it which plane that we're working in and giving it the appropriate YZ or XZ coordinates, we can make it do an arc in any plane. I'm not going to go through all of these, but another one that I want to mention is cutter radius count, which is a way to adjust the cutter size. It gives the operator a little more accuracy of the final cut. And we have G41, which tells it to compensate left, and G42, which tells it to compensate right. And we have that zero code in here, which turns off left and right. So G40 turns off G41 or G42. And then at the bottom we have this group, which is our work coordinate system offsets, WCS. You see that a lot in the software, work coordinate system. That's how you shift your zero from one location to another location. So the most common is G54, but these go up to G59, and then you'll find in some controls they go way beyond that. So it might be G59.001, 0.002, up to 0.999. So you could have, what is it, 1,005 fixture offsets. So there'll be some variation of that. It might say G59.1 P1, G59.1 P2. They all have slightly different ways of doing it, but if you see a 59, it's a work coordinate offset, most likely. So that's a way of shifting zeros from multiple parts and multiple fixtures. So all CNC code is not G code. All machines require the same basic information, but not all the information is going to look the same. And that's the main reason why we have 1,000 post-processors in our library. Because there's always these little minor variations that we have to make. I have written posts before, and I probably have well over 500 post-processors just for Fanuc controls. Because there's all these little variations on how the machine manufacturer could make that same control work on a similar machine. They just have their own way of doing things. X plus does not have to go this way. X plus could go that way. The machine builder can make that control do whatever they want. So because of that, we might have to tweak little things in the post-processors. So to give you an idea of that, the type of information we need is almost always going to be the same, but depending on the machine, it will be formatted differently. So here we have an example of creating an arc or a circular move. So we need to know the starting point. So I'm already at the starting point here with this green dot. I need to tell it the arc direction, clockwise or counterclockwise, which is illustrated with the blue arrows. So I could go clockwise here, doing this arc, or clockwise here, doing this arc, or counterclockwise here or here. And I'm going to this endpoint, which is the red dot. So you can see there's 4 different ways of getting between the green dot and the red dot. But we can narrow that down by specifying a direction and also specifying a center point. So with the center, we can either tell it the center or the actual radius that we want to create between those 2 points. And that narrows it down enough that the control knows what we're talking about. So here's an example of creating arcs the same way for a variety of controls. So the first section up on top is for a Fanuc or a Haas. Their code format is very, very similar. So the first one shows a G2, so circular clockwise. We have an XY destination, where we're going to. We have an I and a J, which describes the center point and our feed rate. So even within the same control, we can do that another way. We can do it as a G2 with an XY destination and a radius, and with the R plus or R minus, we can tell it which direction we're going, whether we're doing the large portion of the arc or the small portion of the arc. So here's another one. This is an analam control. I actually have an analam control on my machine. Analam was known for their conversational format. So if you look at this, it says arc clockwise. There's no big mystery there, huh? We have a pretty good idea what that line's going to do. We're going to go to this XY coordinate, and we're going to rotate around this X and Y center. Pretty clear what that line means, isn't it? That's why they call it a conversational format. You can see exactly what's going on. But even with that control, there's another way of doing the same thing. So we could say arc clockwise to this XY destination using this radius. So again, that tells it another way of doing the exact same thing. And then my personal favorite, which is the hide behind. I love the hide behind control. It's beautiful, very sophisticated, one of my all-time favorites. Here they're doing definition of the circle center. And then on the second line, they're describing a clockwise circle to an XY destination. So they do it as 2 lines of code for this example. Here, it's the same basic thing. Now all these are doing the same arc. So for this one, they're describing the center point again. But this time they're saying circular, polar. The polar angle is 90 degrees, and the direction is minus. So they're doing it with polar coordinates. They're doing a 90-degree portion of an arc. And then the next one, circle radius. We have an X and a Y destination. And we have the direction and the radius. So it's all the same basic information formatted different ways. And that's why we have so many posts. Because people need different things.
Hence the sarcasm.
Except for the changes and differences. So post-processors are translators. They translate the image of the toolpath into the language for the machine. This is where the rubber hits the road. If we don't do this right, we're not doing anything. Because I don't care how beautifully you can model your part and how cool your toolpath looks on the screen, if you can't output it into something that makes a machine cut that part, then everything you've done prior to that is a cartoon. And we don't do cartoons. We make things. So, we need to get the right information out to the machine tool. And these are some of the things that we need in order to get the right information. So if you have a customer with a problem and he needs a post written, this is the kind of information that we need in order to generate a post. Well, we're going to need to know the machine name and model. And we're going to need to know the control name and model. Now, if it's a Haas machine, it's going to have a Haas control on it. If it's an OKK machine, it might have a Mitsubishi control. It might have a Siemens control. It might have a Fanuc control. It might have a Yasnak control. So we need to know which control it is because they're all similar, but they're all a little bit different. We need to know the type of machine, number of axes, and axis designations. So a vertical mill, 4-axis, and it's X, Y, Z, and A. So that narrows down what it is that we're doing this post-processor for. Then we would need a list of the G codes and the M codes for that machine. Normally, in the programming manual that comes with that machine, there will be a single page, or maybe a couple of pages, that will have all the G codes and another one that has all the M codes. That can be enough. For some of the more sophisticated machines, when you start getting into 5, 6-axis lathes and multi-spindles and part swapping and all that kind of stuff, the person writing the post may actually need the programming manual, because there are other levels of complexity to the code that he might only be able to get out of the manual. But for most simple 3-axis machines, that's good enough. Next, a sample program using the post-test part, which is called benchmark. So if you go to the CAM samples folder, there should be a part in there called benchmark. And that's the same part that we use to test all posts. It already has the tool paths in it. So what he should do is just open that part up and post it, selecting a post processor that's going to be closest to what he thinks is his machine. And our posts have pretty good descriptions, so you should be able to figure out which one's going to be most similar to his. He may want to post it through a couple of different ones and look at the code to see which one looks most like his. No one writes a post from scratch. You always take an existing post now and modify it, to get it that extra 10% finished. We also need a sample program that has been successfully run in the machine with no errors. Most machines come with a programming manual, and in the back of that programming manual, there will be sample parts, or sample programs. Those sample programs never work. They just never work. They're always missing something. I've had people send me those as the sample, and then if you write your post to look like that, they're going to send it to their machine, and it's just not going to work. So we need something that has actually been run in the machine with no errors. And I think the no errors part is the particularly important part of that statement. So he picks a post that looks like it's going to work best for his machine, and he posts some code. Now he's going to modify that code to make the obvious changes that he can see need to be made from what he knows about how the machine works. Now he's going to send that program out to the machine, and most likely he's going to have to make some additional changes to fine-tune it. And once he has that complete, and that program works in his machine, he needs to send us this information, along with which post he started with, and that sample program that works. And we should be able to make a post that takes that sample part and gives him that output that he needs. That's about it in a nutshell.